my topic is storage on the grid and for cars. I thought I would talk at a fairly high level. It's kind of introductory but provocative, and make you think about some things that maybe you haven't thought about. We actually do use computing rather fundamentally in ways that it hasn't been used before, and I will spend a little time on that. And I think I'm not going to get very technical about energy storage, a little bit, but not much about what we're actually doing. So let me, because I'm not going to do that, start by saying this thing, which we pronounce, you have to have an acronym you pronounce, otherwise you don't exist. So that is pronounced J. Caesar. And the idea is to, strike awe into the minds of our competitors, but easy to remember. So we are 2.5 years old. It's a 5-year contract with DOE. It's in the Office of Science, actually basic energy sciences. And the idea is to develop next generation storage. So you guys all know about lithium ion. That's what does everything in the world, including these things. But it's not good enough for cars, in spite of the fact that Tesla and others do use it in cars. The drawback is Tesla's pretty expensive. And in fact, the least expensive electric car you can buy is still a lot more than the least expensive gasoline car. So apart from driving my Tesla because I like the way it feels, or I like to show off, or I like the, kind of the open blue sky over my head, if you really want to have an impact on transportation, you have to displace the cheap cars. You need a mass market car. So you need a $20,000 car. And we're pretty far away from that. The other application is the grid. So there's almost no electrical storage on the grid now. There is some pumped hydro. That's what most of it is. And there's only 2% of the storage capacity is about 2% of what we can generate. So it's almost nothing. And that's pumped hydro. But there are lots of reasons why you would want to have storage on the grid. And these beautiful lithium-ion batteries are just too expensive for that. So we have two goals. We want to get a little tiny battery. It's actually bigger than this, but this, gets the point across, that drives you 200 or 300 miles and doesn't cost much. That's the first challenge. And the second challenge for the grid is it can be bigger, because we'll probably put it in a shed somewhere and control the temperature. It doesn't have to work at 0 degrees like your car does. But it has to be cheap for the grid. So those are the two challenges. So Department of Energy was very innovative. And they in fact named what we are an energy innovation hub. There's 4 of them. They're funded at very generous levels. We get $25 million a year for 5 years. And we could be renewed for a second 5 years. We're halfway through the first 5 years, so it's a little too soon to talk about that. But the idea is that we could do something different. So I'm going to spend most of the time telling you about what we do different and why we think it'll work. I won't spend any time unless you ask me. You could ask the potentially embarrassing question, so what have you done in 2.5 years? And because I have to have an answer to it, I do have an answer to it, and I'd be happy to explain that. But that's for the Q&A. So, okay, let's launch. Oh, first of all, if you want to know more, here's our webpage. Stuff on it changes all the time. We have a couple of web administrators that really look after it well. And so it's kind of like browsing the New York Times. Take a look at that. This is a review article that now is a little bit out of date because it's mostly on what we did last year. But there's a URL for it, and if you're a serious person, you can read that. It itself is not very technical. It's mostly high-level stuff. So this is what we all know, right? Lithium-ion batteries, they enabled this personal electronics revolution. And they came out in 1991. They started Sony brought them out. Of course, it would be a Japanese company that had lots of personal electronics to power. That's the reason they wanted it. It was about twice as good in performance as the best battery in 1991, which was nickel metal hydride or nickel cadmium. So this had twice the energy density, which means you could make it half as big and power the same stuff. And it started kind of modestly, maybe music players and camcorders, but take a look at what we have now. So my cell phone, I never make a call on it. I use it to check the web, I text, I do every other possible, I see when is the CTA gonna come or the bus, do every possible thing, and honestly hardly ever use it for a phone call. But wow, it and tablets and laptops and now watches have really changed the way that we interact with people and with information. So when I read a scientific article, I've got Google right next to me. If I don't understand this sentence, I Google the sentence. I read Wikipedia, my favorite source, and I get it. And then I go back to reading. So, I mean, it has really changed. It's also forced us to quit writing, so nobody can write anymore. We can all type, but we can't write. Well, that's a sign of the times. Anyway, these things are wonderful, and lithium-ion batteries made this possible. They've gotten a lot better since 1991. So they're about a factor of 10 cheaper than they were in 1991, and they're about a factor of 3 more powerful. So the energy density is about a factor of 3 higher. So if you take the factor of 2, that they were better than nickel cadmium when they came out in 91, and now the factor of 3 since 91, you're talking a factor of 6 better in performance, and that's starting to make a huge difference. It's still a problem with batteries, though. If you look at your Mac, this is sort of an X-ray picture, and you can see most of its battery. The logic board takes up no space at all. Those things are nanoscale, so you can get all the logic you want in there. And here's the trackpad. What? So yeah, but it's mostly battery. So this is the old version of the Samsung cell phone, and I just updated to a newer one, which has a bigger screen. And they were selling it to me saying, well, the keyboard will be bigger, your fingers won't get in the way, you won't have fat fingers, and you can see things. And so I think the real reason is they need more space for the battery. Because you can put all kinds of apps on the cell phone that you just don't have the power to run. So it's still the limitation. So if we make a better battery for cars in the grid, it will probably spill over into this 20K electric car, and you need grid scale electricity storage. Here's some of the reasons why. You could imagine you want to put wind and solar out there. They're variable. And you have to back them up with something rather than waste the excess electricity. And when you don't have enough, turn on the gas plant, which is right next to the wind farm. Doesn't really make sense. You'd rather store the excess and withdraw it later. Right now it's a little too expensive. So a battery, over the life of the battery, if you store it and release it and so on, it costs to get a certain amount of energy out, it costs about 5 times more than it does to build a gas plant over the life of the gas plant. So that's the competition that batteries face, and that's one of our targets, make it a factor of 5 better. So here's the 2 things that we're going after. We're not there yet. Interesting question. So here's all the energy we used in 2013 in the US. And the 2 biggest sectors are colored. The grid took almost 40% of all our energy is electrons in wires, and 28% is gasoline in your tank. And these 2 things make about 2/3 of all the energy we use. So on this scale, personal electronics is 2%. If you channeled half of the energy through storage, that would be 10 times more than the energy that is put out by lithium-ion batteries. And just as another factoid, reference point, lithium-ion batteries are now about a $15 to $20 billion market. So we're talking about a market that, at least in energy terms, could be 10 times bigger than that. So it's really interesting from a business point of view. Maybe we should try to do this. This is Jay Caesar at the very high level, 1 slide, everything. Here's our vision: transform transportation and the electricity grid with high performance, low cost energy, electricity storage. That's what we'd like. That's going to take, decade, maybe 2 decades to really do. We have a mission. This is much more immediate. We want to deliver within 5 years And we only say 5 years because that's a link to the contract. We did not pick 5 years. We were told you can apply for this 5-year grant. Okay, we'll apply for it. But we want to have some transformational outcomes. So prototypes, not batteries, but prototypes that if they were scaled up to manufacturing would have 5 times the energy density of lithium-ion batteries and cost 1/5. So the cost 1/5, that's for the grid, 5 times the energy density, that's for the car. Although they both interact with each other in both cases, but that's the basic breakdown. So that's aggressive. And that is, I don't know, you may call it aspirational. We're shooting high. But we know from experience, if you don't shoot high, you don't get very far. Can we do it in 5 years? I don't know, maybe not. We're halfway there and we have some light at the end of the tunnel that we think maybe we can. And if it takes longer, well, maybe we'll get renewed. So we want to achieve this. We want to leave 3 things behind, 3 legacies, and we'll use those legacies to actually achieve our goal. Here's the first one. Library of Fundamental Science of the Materials and Phenomena of Energy Storage, it means electricity storage, at atomic and molecular levels. So we've had maybe 15 years of nanoscience, or at least the word nanoscience. And this, honestly, has not been applied to electricity storage anywhere near the level that it should be or could be. So let's actually understand at this atomic and molecular level what happens. And we want to do that for 2 reasons. Because we feel if we really understand how these things work, we can identify the next material that we'll need for the next generation battery much more quickly and effectively because we kind of know what we're looking for. And once we identify it, we can get the most performance out of it, again, because we know what we're looking for. So we think this is basic. Then the next thing we'd like to leave behind are these 2 prototypes, and they'll probably look really different. So the car will be a small thing you put under the hood, the grid thing will be big. But they may be based on the same set of fundamental knowledge that we developed in Legacy 1. That's in common. And the third thing may turn out to be the most important thing. A new paradigm for battery R&D. So the way the battery community now works, I'm in a research group at a university. I find a material that might be a cathode, the next generation cathode, and I publish it. I'm done. Somebody has to come along somewhere else, maybe in a company, a startup company, or another engineering department, and say, I think I can make a cathode out of that, and I'll try to make a cathode. He's done. Then the next group comes along and says, well, I think I can make a battery with your cathode, but I have to combine it with an electrolyte with an anode, and maybe I can do this integration, and that's a third group. These groups don't usually talk to each other very much. They communicate through the literature, and they have different motivations. I'm a scientist. I want to make my discovery. I want to publish my paper in Nature. Give me 10 Nature papers, and I'm good for 5 years. That is not the way technology works. They want to bring out a product, and they just have different motivations. So we want to combine 4 things, and they're listed here, 4 things, in one organization. So it's discovery science, battery design, research prototyping for batteries, and manufacturing collaboration. We're not going to manufacture. We don't know how to do it, and we don't have enough money, and so on. Other people do it better. But we'll talk to the manufacturers, and that's really, really important. So here is
My question doesn't really affect the legacies because even without that, the legacies are really transformational. But do you think your vision is enough? Do you think 5X is enough? Don't you think there needs to be a disruptive technology to displace oil and gas?
Yeah, absolutely.
Do you think that you need at least 10x, not 5?
So, great question. So you might say, why stop at 10? So there's 2 reasons for that. One reason is we don't know that there exist materials that will be better than a factor of 10. So I can think of several cases, and the whole community does this all the time. On the back of an envelope, I just say, let me take lithium and oxygen, and here's the reactivity and so on. Looks like it's a factor of 10. So a factor of 5 is about half theoretical in that case, and that's thought to be achievable. You can do half. So one reason is there may not be materials that can do better than on the ground a factor of 5, theoretically a factor of 10. The other reason is that if we shoot too far in the future or beyond where we are, we don't know how to get there. And I'm going to show you some slides that indicate how we think we're going to get there with this factor of 5. That could be, in principle, the platform for another factor of 5 later on. But maybe we're just modest. And we're only, I mean, this is in fact transformational. So if you could get these factors of 5, you would pretty much have 30% electric cars, and you would have grid storage everywhere. So this would already be a big.
Well, it's 2 factors of 5 because of the cost.
Yeah, it's 2 factors of 5, but they are related. So if I make a battery that's 5 times smaller with the same energy density, then I don't need as many materials, and you might say I'd automatically get a factor of 5 in cost. I mean, back of the envelope. But they are definitely additive, yeah. So
What's the environmental impact of these batteries? I mean, could it be that once you've built a large battery for storing electricity, it would actually be better from an environmental point of view to use the gas power plant instead of storing the electricity in the battery?
So there are studies of that. So we don't know for the batteries we're making, which are next generation. I mean, we don't know what they are, so you can't say what the environmental impact is of making them. But for lithium-ion batteries, it's really clear that, for example, making a lithium-ion battery that would replace a coal-fired power plant, you're better off with the battery. So certainly from an emissions point of view, if these things enable wind and solar to be widely deployed, let's say at the 20 or 30% level instead of the 4% level where they are now, that's a big win environmentally. And the batteries that we know of now, and we could expect next generation batteries won't be much different, that it's kind of a no-brainer for that. You can think of other environmental impacts, and indeed, so the lithium-ion battery has expensive cobalt in it. It has organic electrolytes, which can catch fire, as Tesla and Boeing found out. And there are impact. What if they leak out and so on? And you have to take those things into account. Actually, we do. We think of, I'll show you in a minute, all the materials we're looking at, and we tend to look at only those things that have a certain level of safety. So we don't go with the things that might work great, but are clearly unsafe. Just don't go there. But that is a very, very important question. Before I go back to my slides, I'm going to, yeah.
Is there any consideration in improving the lifetime of the battery?
If you double the lifetime, you cut the cost in half. So absolutely. And one of the questions the lithium-ion community faces, and we face too, is why does it go bad? And I'll show you in an animation, lithium ions are moving from anode to cathode to anode, so they have to go in, they go out, things swell, they shrink, eventually they fracture. And the electrode itself just has 1,000 cycles in it or 6,000 cycles in it, and it just degrades. And so can you double that lifetime? Why not? If you really understand things at the atomic and molecular level, and if you maybe take a big block of electrode that's this big and has to expand to this big, and you shrink it down to 10 nanometers, it can actually be flexible enough to shrink and grow and not fracture. So there are ways to think about that, for sure. So here's our paradigm. Here's the 4 things. You see here in the red, this is the discovery science part, 3 labels, which I'll tell you about in a minute. Never mind what they are, but those are 3 concepts that we're following. And we could apply those concepts. I'll show you in a minute. A battery has a cathode, an anode, and an electrolyte. We can apply these concepts at the cathode or at the anode. So it's really 9 different kinds of batteries here, 3 times 3. Lots of cross-cutting science. We do battery design and so on. We bring some special tools, and one of the tools we bring is computation, being used in a new way. So here's a thing on the discovery science side, materials project and electrolyte genome. So the idea of a materials genome, that's the vernacular, is that I'm looking for a new cathode. I have some ideas about what might be a good new cathode. Instead of making those things in the laboratory, I'll simulate them on a computer. And with a computer, I can do it so fast, I can, in a sense, go crazy. I can simulate 10,000 different cathodes that I think might work. Then I look at them all on paper or on the screen, and I choose maybe 10 or 20 that really look promising, and I throw the others out. So that idea has been around, predates J. Caesar by 5 or 6 or 7 or 8 years. And people have applied it to battery electrodes, as we do, but we've taken it a step further. We've probably done more, and we have the infrastructure, computational infrastructure and databases and so on, to really do it at industrial scale. So that's for crystalline electrodes, and you use things like density functional theory and so on. It's a perfect crystal, and I want to know all the electronic structure properties. I want to know how fast lithium goes in and comes out, and I'll show you in a minute why that's important. Those things can be calculated. We added another feature, and that's the second screen you see there, the electrolyte genome. So every battery has a liquid electrolyte in which the lithium ions dissolve and going from anode to cathode. Lots of organic electrolytes around, molecules that could be electrolytes, that simply are not used and are too complicated. Nobody knows what they are. We tend to concentrate on maybe 15 different electrolytes, organic electrolytes, and just ignore the rest. Why don't we look at those things? So we have now done the same thing for liquids. It's a different kind of calculation. You worry about different properties. And we've taken it to the extreme. We just completed, after 2.5 years, a catalog of 16,000 organic molecules that could be used for electrolytes. And now we have the challenge of sifting through all that stuff. We've sifted through some of it, but it's a gold mine. So we simulate before we make in the lab. It saves enormous amounts of time, and it lets you pinpoint, you hope, the things that are going to work and throw away all the things that won't work. So that's one way in which we use computers. Second thing we have is quite experimental. So in a battery or in any electrochemical device, it's the interface between the crystalline electrode and the liquid electrolyte that counts. That's where all the electrochemistry takes place. It's where the energy storage and releasing takes place. So we can synthesize those interfaces. We can use state-of-the-art tools, X-rays, infrared, scanning tunneling microscopes, all kinds of things to study what happens at that interface. So this is critical, actually. And I believe, to our knowledge, it's the best, well, it competes with the best in the world. Then we use another computation in another way, very similar to the way that we use it for materials, except here the object is the whole battery. So I'll show you in a minute. It's anode, electrolyte, cathode. How do they work together? And you find typically, in most cases, they don't work together. You have to look for the cases where they work together. So we look for those cases, and we project, if I were to scale up this idea to a manufactured battery, what would it cost? So that's one of our 2 5s. What would it cost? Would it be a factor of 5 less than now? And how would it perform? Would it perform a factor of 5 better than today's batteries? So we can, again, ask these questions on the computer before we actually make the battery. That saves an enormous amount of time, and we hope trashes 80% of the things that we would like to make that this techno-economic modeling tells us probably won't work. And we'll concentrate on the ones that do. So this is a second way in which we use computation. We also have, when organizing our research, a thing called sprints. So almost every prototype has maybe 5 critical questions. You have to answer yes to these 5 if that's going to work. We'll take the top question, the most important one. We'll formulate the question in a very precise way so it's limited. We'll form a team. So we have $25 million a year. We have 14 institutions that are part of J. Caesar. We have maybe 160 researchers at those institutions, including postdocs and graduate students. We'll take a team of maybe 5 to 15. The team is tailored to answer that question, and we'll give them maybe 2 months or up to 6 months. Give me an answer. If it's yes, we'll go on to the next question. If it's no, at least in principle, we'll trash that idea or we'll try something else. So it turns out this is a very, very good way to punctuate the research and structure it. Everyone knows what they're doing. And I will tell you, this audience may like this better than Paul will, that the sprints that are led by early career people, including postdocs, usually do better than the ones that are led by senior people. Because the early career folks are really engaged. That's pretty much all they're doing, at least for that 6 months. Whereas the senior people have got 100 things on their mind, and I'll get around to the sprint, maybe tomorrow, and it goes slower. So it's a great leadership experience because the sprint is over. So if it worked great, you feel good. If it didn't work so good, it doesn't hang over your head for the rest of your life. You move on to the next thing, and you try again. So it's really quite a nice thing. Okay, so how does a battery work? And this is the thing that will, that will sort of explain why we're doing what we're doing. So here's the battery. There's an anode over here. It's usually graphite. For lithium ion, it's graphite. There's a liquid organic electrolyte here. There's an interface layer that appears because the electrolyte reacts with the graphite and makes this layer. On the other side, there's a cathode, which is also layered for lithium-ion batteries. It's typically a metal oxide, so cobalt oxide, dioxide. It also has an interface layer from reactions. And we're now looking at the charging state. So the lithiums are stored in the cathode when it's discharged. To charge it, you put on a voltage and drive them over to the anode. They exist in between the layers of the graphite, so that's called intercalation. And so if you're discharging, a singly charged lithium ion leaves the intercalation host, graphite, goes through this layer. You see the plus sign. It acquires the solvation shell of the polarizable organic molecules. So they're neutral, but they can be polarized, so they get a dipole and the minus sign points in toward the lithium. And it goes over to the cathode. And so this thing just goes back and forth. So sometimes it's called a rocking chair battery. So the lithium ions are in the cathode, they're in the anode, they're in the cathode, they're in the anode. It's storing energy, it's releasing energy. It just goes back and forth. And this was the great advance in 1991. So what are we going to do something better than lithium ion? So here they are. As I said, there were three things. So there's the lithium ion battery. First thing we are going to look at is lithium has one charge on it. So why don't I use magnesium, which has two charges? Calcium has two charges. Zinc has two charges. Aluminum has three charges. So at least in principle, order of magnitude, I've doubled or tripled the energy stored with each cycle of that magnesium compared to lithium. So great idea. This idea has been around, not ours, not original with us. The trouble with the idea is that none of the anodes, cathodes, or electrolytes that work for lithium also work for magnesium. So you have to discover three new materials that are compatible with magnesium. But in principle, a very good idea. Second idea is get rid of intercalation. You may have noticed that even when there's no lithium in the anode, in the graphite is still there. It's taking up space and it weighs something. So I can make the energy density of the battery higher if I didn't have this host, kind of neutral, non-active host sitting around. Okay, so I'll have a pure lithium metal anode, and I'll have sulfur as the cathode, and when the lithium goes across to the sulfur, it makes a chemical reaction, a covalent chemical bond. And you can store a lot more energy in a high energy covalent chemical bond than you can in intercalation. So this is where you get the estimates of factors of 10 if that were oxygen, for example, and similar for sulfur. Trouble, sulfur's an insulator. The Li2S, which forms with lithium, is also an insulator. So it's pretty hard to make it go backwards. You can't access these insulators electronically. You could do it with temperature, but you don't want to be heating the thing up. There are ways around that, but that's the basic challenge. Third idea, get rid of the crystalline electrodes altogether. So make them a liquid. So make it either a solution of ions in solution, or make it a suspension of nanoparticles floating in the liquid. Why do you want to do that? Well, first of all, you can scale that up to the size you need for the grid rather easily. You just make the liquid tanks as big as you need to make them. And the idea is of the flow battery, as this is called, is there's a reactor here. The active ions on one side react with the active ions on the other and exchange, form chemical reactions and exchange energy, and the electrons go through the external circuit. So this part stays the same and the tanks grow. So another reason we like this, typically these batteries are around. They're made with vanadium or some transition metal, but you can make them with organics. And organics are things, of course, like hydrogen, carbon, nitrogen, oxygen, stuff that's cheap, that's abundant, that at least in principle, if you recycle it back to elemental form, is harmless to the environment. And the prospect of doing this on a big scale really cheaply and recycling everything is pretty appealing. So those are the three ideas. And I want to, yes?
Combine the two on the right side?
Of course.
And use some reactive thing? Some reaction of a metal that melts or solidifies?
Absolutely. So you could have a lithium metal anode, so that's crystalline, and you could have a fluid electrode, which might be something that contains sulfur in solution, for example. So you can certainly combine. You can combine this one also. I could have a magnesium metal anode instead of this intercalation, and maybe have an intercalation cathode. So the nice thing about this is precisely what you're saying. It looks like 3 ideas. It's 9 ideas, because every one of them can be done at the anode or the cathode. Yeah.
So your comment a moment ago suggested that maybe it's hard with the traditional batteries to scale them up. Why is that?
Just because, so I'll give you an example. Tesla uses Panasonic computer batteries, 7,000 of them. So the way he scales up is just, if you open it up, there's 7,000 little tiny cells this big in there. And that's because it's hard to scale up. So once you figure out how to make it, you really don't want to retool everything to do that same process at, say, 100 times scale.
But is there some sort of chemical reason why that's difficult?
Well, in a way, yes. So right now, everything is done with thin films. And I was mentioning earlier that the reason batteries fail is the lithium has to go in and out of the anode and cathode. If it's a big thing, the shrinkage and the growth gets to be a real problem. If it's a thin film, then you can better live with it. So it's sometimes just making something 10 times bigger makes it impossible to do by the same techniques. So yeah, good question. So this is now really important, and it's kind of the last important thing I'm going to say. But I want to compare lithium ion with beyond lithium ion. So I've got 2 axes here. Systems, and by that I mean, what's the concept? For lithium ion, it's intercalation at the anode, it's intercalation at the cathode. It's really simple. It's one concept at both electrodes. Here I've got materials. Well, almost every lithium-ion battery has a graphite anode. 90% of them have a cobalt oxide cathode. But you can talk about other cathodes and other electrolytes, and there might be probably between 5 and 10 different materials that you use to make lithium-ion. It's been around since 1991, so we know a lot about it. It's already gotten a lot better. I was saying a factor of 3 in performance and a factor of 10 in cost since 91. There's still improvements you can make, but they're incremental. You will not get the transformational factors of 5 that we want from lithium ion. You can, on the back of an envelope, you can just prove to yourself right away it won't work. Here's beyond lithium ion. It's a way, way, way bigger space. We were saying that there are 3 ideas you apply at the anode or the cathode. The electrolyte could be liquid, it could be solid, so there's 18 different ways to conceptualize the beyond lithium ion battery compared to 1 for lithium ion. If you look at the materials, there's maybe 30 or 40 different materials that are being considered to implement those 18 ideas, which means that you can make a lot of batteries in this space. So very conservatively, I wrote there 50 to 100. I showed this slide at a meeting, and one of our J. Caesar members, in fact, was in the audience. He said, that's wrong. It's not 50 to 100, it's 500 to 1,000. And maybe it is. But let's be conservative. I'd say it's 50 to 100. When you're faced with a space this big, you cannot be Thomas Edison. So you can't say, well, I'll try the first one. If that doesn't work, I'll try the second one. And 2% inspiration and 98% perspiration, I'll eventually get there. Well, you probably won't. So, and I didn't mention this, but the history of lithium ion is that most things don't work. The simple, elegant idea is perfect, like all these 3 ideas I was showing you. And when you go to do it, you realize, oh, there's 5 things that I thought might go wrong, and every one of them goes wrong. And then there's 5 more that I didn't even think of, and they also go wrong. So what you're faced with is overcoming a series of problems that side effects that you have to fix. And that usually defeats most things. Well, it didn't defeat lithium ion, that's good, and there's some solutions in this space that it won't defeat. But what I was saying earlier, faced with this big space, you have to trash 80% of it at the beginning and go after the 20% that looks like it might work. We do that partly through computation. So we look at the materials and we look at the battery systems and we analyze them rather deeply before we ever start to make them. And we can then start with the ones that look, let's say, the most promising. So I'll say one more that's not as important as what I just said, but sort of important. So what kind of a battery are we going to make? We had our first review 8 months after we launched. It was a serious review with 7 outside reviewers and our DOE program managers and so on. And one of the reviewers asked or said, oh, you're making a prototype. So you'll put it under the hood of a Chevy Volt, you'll drive it around for a couple of months to see if it works. And we said, no, that's not what we're going to do. Too expensive and just too big a job for us. We'll make a prototype that I can hold in my hand. It might look kind of messy. It may have wires hanging off like this. It might be a little more polished and packaged like the thing above it. But it will be small. We'll use our data from this prototype and techno-economic modeling to predict how would it behave if we scaled it up. And we'll hope to interest a manufacturer such as Johnson Controls, which happens to be the biggest manufacturer of lead-acid batteries. And remarkably, they've been around for 100 years. They still start everyone's car. It's a big business for them, but they would like to get in on the next part of the business too. So we talk to them quite frequently, and we ask them, what kind of a prototype do we have to make to interest you in making, say, a thing like that, which is the battery of a Chevy Volt, that you could put under the hood of a Volt and drive it around and see if it works. And the argument we have with them is they say, make it big. And we say, can't make it big. So we argue back and forth about how big is big enough, and we've reached I'll call it a happy medium. It's at least a medium. And we realized that their sort of product prototypes start from here and get bigger and more complex. We start from here, and our top level research prototypes overlap about 2 rungs of the ladder. So the last time we were up there, which was earlier this spring, we agreed that when we get close to those 2 rungs that overlap, we'll start working with them. And they can tell us, this is never going to scale, forget it, or don't use this material, it's, you can't make enough of it, or whatever. And this kind of advice is really, really helpful, because most scientists never think about how would I commercialize this. They just think, hey, here's an interesting discovery. And when you look at the whole chain, you can really save a lot of time. So I think that's the last thing I'm going to say. And yeah, thank you. Yeah. Oh, here's a question. Yeah.
What tools or libraries that you use for simulation?
A lot, so there's, well, for the electrodes, it's a lot of density functional theory. So we want to know the electronic structure. Is it stable? So I've got a compound that I think would be great. Can you even make it? You know, is it stable? And we'd like to know if it's an intercalation, you want to put, let's say, magnesium in it. Will magnesium go into it? You know, is it stable with magnesium in it? If I put 1% magnesium or 100% magnesium, is there a phase transition to some other crystalline phase, which we actually don't want? So we'd like to find something that has just one phase like graphite does, and you put as much stuff in between as you like. Questions like that. For the liquid, you want to simulate liquid behavior, and that's more molecular dynamics. So you have all these, you have, let's say, hundreds or thousands of molecules, all the same, but you want to let them interact, and you need an interaction potential, which you get from someplace, and you can probably refine by experiment. And once you get that interaction potential, then at least in principle you can calculate or simulate what that liquid would do if there were a positively charged, let's say, magnesium ion there. So it's a variety of things. And I think the advantage of what we do is that with the team we have and the 14 institutions and so on, we can actually cover every phenomena that occurs in a battery. A research group would never be able to do that. Even one institution would have trouble. Toyota could do it. GM could do it, but they're not many. And so we bring this, the whole is bigger than the sum of the parts idea. Do you want to?
So I have a couple of questions. So first question is just to get your thoughts on, say like in 5-10 years time, if you went to that goal of 30% of cars being battery or electric, what impact would that have on, like, would lithium or whatever the material is the battery, would that become the next oil?
Yeah.
I mean, I understand you can recycle these things. It's not like oil that you just burn it, but have people thought about that? Like, where does this lithium come from? What's the energy security aspect of it?
Yeah, that's a great question, and people have thought about it. So a lot of it comes from South America, lithium. And I think there's enough lithium around right now, not talking about 30% car penetration, but right now, that you don't worry too much about finding the rest of it, which is somewhere. But careful studies have shown, and people have done this, especially for lithium-ion batteries, because we know everything about them, you can recycle them. You more or less have to recycle them, because if you threw away the lithium every time the battery went bad, there wouldn't be enough lithium. But if you do recycle, as you said, then you can make it live. And even with 30% penetration, to the best you can estimate, it works. But you do have to recycle for sure.
So my second question is then, again, related to 30% penetration.
Yeah.
What impact would that have on the electricity grid? Because, I mean, the grid is probably like decades old, right? And it's designed to protect itself. So
Yep.
if everyone were to plug in their Chevy Bolt or the new small car that comes out, won't the grid just shut down? And I know people are studying this, just to get your thoughts on.
Yeah, so it depends on what time of day everyone plugs it in at the same time. If it's 6 in the afternoon, the grid's dead. If it's 2 in the morning, the grid's fine. It turns out there are studies of this, that 70% penetration of electric cars could easily be charged with the excess capacity on the grid, mostly at night, if everybody chose to charge at night, which maybe they would. I mean, that's not unreasonable. So, and it's a fascinating question. The regulators tell the grid operators, don't let the electricity go off, ever. If you let it go off, we're going to really make it painful for you. And this lesson has been learned very well over many decades. So they build everything for the peak. They have no choice. And since you can't store electricity, you have to use it at the same rate you produce it. If there's a really high demand, they can meet that demand. And that means there's plenty of excess to charge cars if you do it intelligently.
We'll take one more.
With the announcement of President Obama, I think yesterday or 2 days ago, about trying to reduce all carbon emissions by 30% and shutting down coal. So did you receive a phone call saying you better give us or are you feeling more pressure, or actually it's better for you to?
Well, so the climate is a whole nother wonderful can of worms. But it's quite clear that people who have thought about this, and it doesn't take you very long to come to this conclusion. It's not, rocket science. But certainly, if you have wind and solar on the grid instead of coal, you're way better off for climate and for carbon emission. You can't really we have about 4% wind and solar on the US grid now. If it were 30%, which is one of the goals you hear, actually California and New York want 50% renewable electricity. So if you have all these generation sources around, you have to have storage. And you hear Terry Boston is the CEO of PJM, which is the ISO, as it's called, that does New England and Chicago. And in his talk, he has a slide that shows wind and solar stuff, and he says, if you like wind and solar, you're going to love storage. So you really have to have it. Does it make us? It makes us feel good, I think. It means maybe we'll be around, we storage guys, will be around for the next 20 or 30 years because the problem will not be solved very fast.